There is a picture of the Milky Way that almost everyone recognizes. A bright central bulge, a flat disk, curving spiral arms traced by blue stars and dark dust lanes. Somewhere between two of those arms, a tiny marker says, "You are here." It looks like a photograph. It cannot be. No camera has ever traveled far enough from the Milky Way to turn around and photograph our galaxy as a whole. Every spacecraft built by humans is still effectively inside the same tiny neighborhood from which we began. Even the most distant probes have crossed only a negligible fraction of the distance that would be required to see the galaxy from above its disk. The familiar face on Milky Way is therefore something more interesting than an image. It is a reconstruction, and that reconstruction is still unfinished. This is the first difficulty in mapping our own galaxy. We live inside the thing we are trying to measure. The Sun sits roughly 27,000 light-years from the galactic center, embedded in a broad stellar disk that extends tens of thousands of light-years in every direction. We do not look at the Milky Way the way we look at Andromeda as a single object suspended in front of us. We look along it, through it, and across it. From Earth, the galaxy is not a spiral, it is a band. That band is the combined light of enormous numbers of stars concentrated near the galactic plane. The spiral structure, central bar, warped outer disk, and distant far side are hidden inside that narrow projection. Imagine trying to determine the floor plan of a city while standing on one street, with buildings blocking one another for miles. Nearby structures can be measured in extraordinary detail. Farther away, entire districts overlap in the same direction. Distance becomes the missing dimension. For the Milky Way, there is an additional obstruction. The space between stars is not transparent at every wavelength. Clouds of interstellar dust absorb and scatter visible light, especially along the crowded galactic plane. In some directions, particularly toward the center, optical telescopes are not simply seeing a dimmer version of what lies beyond. Large parts of the view are heavily obscured, so astronomers learn to change the kind of light they use. Infrared radiation can pass through much of the dust that blocks visible wavelengths. Radio observations can trace cold hydrogen, molecular gas, and compact masers associated with star formation. X-rays reveal energetic environments that ordinary starlight does not. Each wavelength removes one kind of blindness while introducing its own limits. The result is not one map of the Milky Way, but several overlapping maps of different components, each built with a different measuring system. Stars are another problem entirely. A point of light gives a direction on the sky. It does not automatically give a distance. Two stars that appear next to each other may actually be separated by thousands of light years. If the galaxy is going to be reconstructed in 3 dimensions, those distances must somehow be measured. For nearby stars, one of the cleanest methods is parallax. As Earth moves around the Sun, a nearby star appears to shift slightly against more distant background sources. The angle is tiny. The smaller it becomes, the farther away the star is, and the more demanding the measurement. This is where Gaia transformed galactic astronomy. Launched by the European Space Agency, Gaia repeatedly measured positions and motions across the sky with extraordinary precision. Its third major data release contained astrometric information for well over 1 billion sources, with detailed motion, velocity, and astrophysical data for important subsets. Instead of treating the Milky Way as a luminous band, astronomers could begin examining it as a moving 3-dimensional system. Stars with positions, proper motions, spectra, ages, chemical signatures, and velocities. Yet Gaia did not solve the map. Its science observations ended in January 2025 after more than a decade of scanning. The measurements are still being processed into increasingly rich data releases. More importantly, even a catalog containing more than 1 billion sources represents only a sample of the galaxy, and that sample is not equally complete in every direction. Dust removes stars from optical surveys. Crowding makes measurements harder. Faint stars disappear first with distance. Parallax uncertainties grow as the apparent shifts become smaller. The far side of the disk remains much harder to chart than the region around the Sun. This creates a peculiar reversal. We can observe external galaxies millions of light years away and immediately recognize their large-scale forms. We can see disks, bars, rings, and spiral patterns. But in those galaxies, individual stars are usually far harder to locate and measure with anything like the precision available in our own neighborhood. Inside the Milky Way, we have the opposite problem. We can measure astonishing detail, sometimes down to the motion and chemistry of individual stars, yet assembling those local measurements into one reliable face on picture is difficult. Closeness gives us detail. Closeness takes away perspective. That distinction matters because the Milky Way is not a rigid drawing. Its stars orbit, its spiral features do not behave like painted stripes on a disk. The central region contains a bar whose size, orientation, and dynamical relationship with the surrounding disk must be inferred from stellar distributions and motions. The outer disk is not perfectly flat. Different tracers emphasize different structures. Young hot stars outline recent star formation. Cepheid variables can trace parts of the disk over large distances. Radiomasers in high-mass star-forming regions can provide exceptionally precise geometric distances. Neutral hydrogen reveals structures that may be difficult to follow with starlight alone. Put those tracers together, and a recognizable galaxy emerges. But not every tracer draws exactly the same picture. That is why even a seemingly simple question, such as how many major spiral arms the Milky Way has, requires a careful definition of what is being traced. Gas can emphasize one structure, young stars another. Older stellar populations may be distributed more smoothly. A feature that looks like a continuous arm in one reconstruction may become a set of segments, branches, or spurs when viewed with another population. The map, then, is not merely incomplete because astronomers have not observed enough stars. It is incomplete because the object itself is complicated, because our measurements have selection effects, and because translating what we observe from inside the disk into a view from above requires models. That word is important. A scientific model is not a guess added where the evidence runs out. It is a framework that connects measurements that cannot be viewed from a single external perspective. A distance measurement anchors one point. A velocity adds motion. A spectrum reveals composition or radial speed. A radio survey traces gas. Dust maps estimate which regions are being hidden. Orbital models test whether the reconstructed structure behaves consistently with gravity. The face on Milky Way appears only after these different forms of evidence are combined. And that means the famous spiral diagram contains several levels of certainty at once. Some landmarks are measured with remarkable precision. The location of the galactic center can be tied to the motions of stars orbiting the compact radio source associated with the central black hole. The sun's distance from that center is known to within a small fraction of the galaxy's scale. Nearby stellar structures can be charted in exquisite three-dimensional detail. Other regions are less secure. Dust still blocks optical surveys. The far side of the inner galaxy is difficult. Distances to gas clouds can depend on models of galactic rotation unless a direct geometric method is available. The continuation of spiral features across hidden regions may have to be inferred rather than followed continuously. So the map on the wall is not wrong. It is a compressed statement of evidence. The real question is how that evidence was assembled, which parts are direct measurements, which parts depend on tracers and models, and where the confidence begins to thin out. Because if we remove the clean spiral drawing and keep only what humanity has actually measured, the Milky Way looks very different. It becomes a galaxy built outward from our position, point by point, wavelength by wavelength, with some regions dense with information and others fading into uncertainty. And the first missing piece is the most basic one of all: distance. Distance inside the Milky Way is not measured with one ruler. There is no single technique that begins at the sun and continues cleanly to the opposite edge of the disk. Instead, astronomers use a chain of methods, each reliable over a different range, each tied to different kinds of objects, and each carrying its own uncertainties. That chain is one reason a galactic map can look more definite than the measurements beneath it. Start with the most direct geometric method. Parallax works because Earth changes position as it moves around the Sun. Observe a nearby star at one point in Earth's orbit. Observe it again roughly 6 months later, and the star appears to shift against more distant background sources. If the geometry is known and the angular displacement can be measured, the distance follows without needing to know what kind of star it is. For the nearest stellar neighborhood, this is extraordinarily powerful. But the signal shrinks with distance. A star 1 parsec away has a parallax of 1 arcsecond. Move it 10 times farther away, and the angle becomes 10 times smaller. At 1,000 parsecs, the parallax is only 1,000th of an arcsecond. At still greater distances, the apparent shift becomes so small that instrumental calibration, source brightness, crowding, and systematic effects become increasingly important. Gaia pushed this technique across a remarkable fraction of the Milky Way. But measured by Gaia does not mean that every star in the catalog has an equally precise distance. Nearby bright stars can have excellent astrometry. Faint, distant, obscured, or crowded sources can be much less certain. And there is another subtle point. Astronomers do not always convert a measured parallax into distance simply by taking its mathematical inverse. When the uncertainty becomes significant, that shortcut can produce biased or misleading results. Distance estimates may instead use statistical methods that combine the measurement with prior information about stellar populations or galactic structure. The resulting distance is still grounded in observation, but it is no longer a purely geometric number obtained without assumptions. This is the first place where the map begins to become layered. Some distances are almost direct geometry. Others are estimates constrained by geometry and statistics. Still others require entirely different methods. That matters because many of the most important structures in the Milky Way are much farther away than the stars for which optical parallax is easiest. One solution is to search for objects whose physical properties allow their distances to be inferred from their brightness. Certain variable stars are especially useful. Cepheid variables change brightness in a regular cycle, and the period of that cycle is related to the star's intrinsic luminosity. Measure the period, account for effects such as extinction and calibration, compare the star's true luminosity with how bright it appears from Earth, and the difference provides an estimate of distance. RR Lyrae stars perform a similar function for older stellar populations, although with different calibrations and typical luminosities. These stars become distance markers embedded inside the galaxy. But now another source of uncertainty enters the problem: dust. If a star appears faint because it is far away, that is useful information. If it appears faint, partly because interstellar dust has absorbed some of its light, the same observation can imitate a greater distance. Astronomers must separate the two. Dust does not dim every wavelength equally, so observations across multiple colors can estimate how much light has been removed or reddened. Infrared observations help because longer wavelengths penetrate dusty regions more effectively than visible light. But the distribution and properties of dust are themselves three-dimensional structures that must be mapped. This creates a circular-looking problem. To determine a star's distance, astronomers need to understand the dust between the star and Earth. To locate the dust in 3 dimensions, they often use stars whose distances must already be estimated. The problem is not impossible. Large samples, multiple wavelengths, stellar models, parallax anchors, and statistical reconstruction allow the two to be solved together. But the process reveals something important about galactic cartography. A missing region on a map may not mean there is nothing there. It may mean that the objects normally used as tracers are difficult to detect through that particular line of sight. Nowhere is this more obvious than toward the galactic center. From Earth, the center lies behind enormous amounts of interstellar material. In visible light, the route into the inner galaxy is heavily obscured. Yet, the central region is one of the most important anchors in the entire galactic map. So astronomers approach it in wavelengths that can pass through the dust. Near-infrared observations have tracked stars orbiting extremely close to Sagittarius A star. the compact radio source associated with Milky Way's central supermassive black hole. Those stellar orbits do more than reveal the black hole's mass. Their geometry also helps constrain the distance from the Sun to the galactic center. This value becomes fundamental because almost every large-scale description of the Milky Way depends on the galaxy's coordinate system. Where is the center? How far are we from it? How fast is the Sun moving around it? How does material at other locations move relative to that reference? A change in any of these parameters can propagate into the inferred positions and motions of distant structures. And this leads to one of the most common indirect distance methods in galactic astronomy. Gas in the Milky Way rotates around the galactic center. If astronomers measure the velocity of gas along our line of sight, and if they adopt a model for how rotation speed changes with distance from the center, then that velocity can be used to infer where the gas may be located. This is known broadly as a kinematic distance approach. It sounds straightforward. It is not. The method depends on the assumed galactic rotation curve. Real gas does not follow perfectly circular orbits. Spiral structure can introduce streaming motions. The central bar can perturb velocities. Expanding shells, supernova remnants, stellar winds, and local cloud motions can push material away from the idealized pattern. And for locations inside the Sun's orbit around the galactic center, the same measured radial velocity can often correspond to two possible distances along a single line of sight: a near distance and a far distance. This near-far ambiguity has complicated maps of molecular clouds and star-forming regions for decades. Astronomers can break the ambiguity using additional evidence: absorption against background radio sources, associations with objects of known distance, extinction measurements, maser parallaxes, or other geometric constraints. But notice what is happening. A cloud appears on the sky. Its radio spectrum gives a velocity. A model converts that velocity into possible locations. Other observations decide which location is more plausible. A point is finally placed on the map. Multiply that process across thousands of regions, and a spiral structure begins to emerge. The resulting map may look clean. The route to each point is not. Some of the best anchors come from a very different kind of radio source. In regions where massive stars are forming, molecules such as methanol or water can produce extremely bright, narrow radio emission through the maser process. These masers can be observed with networks of radio telescopes separated by thousands of kilometers. By combining those telescopes through very long baseline interferometry, astronomers can measure positions with extraordinarily fine angular precision. That allows parallax measurements far beyond the distances where ordinary optical work is easiest. A maser associated with a distant star-forming region can therefore provide something precious: a geometric distance to a specific piece of galactic structure. It can also provide proper motion. Add the source's line of sight velocity, and astronomers begin to recover its full three-dimensional motion. This turns certain star-forming regions into fixed survey points along the Milky Way's spiral pattern. Projects using radio interferometry have measured such regions across large portions of the disk, helping constrain the shape of spiral arms, the galaxy's rotation, and the Sun's motion. These measurements are among the strongest evidence that the Milky Way possesses organized spiral structure. They also reveal why drawing that structure is harder than it appears. The measured sources are not spread evenly across the disk. They tend to mark regions where suitable masers exist and where radio observations can isolate them. They trace recent massive star formation, not the entire stellar mass of the galaxy. A spiral arm defined by gas and young stars is not necessarily identical to a feature defined by older stars. The tracer determines part of the picture. This is why astronomers rarely ask only, where are the spiral arms? A more precise question is, which population is tracing which structure? Young massive stars do not live long enough to wander far from where they formed, so they can mark recent star formation. Molecular clouds show where cold gas has accumulated. Atomic hydrogen reveals gas on a much larger scale. Cepheids trace relatively young stellar populations across significant distances. Older red giant stars show a smoother underlying stellar distribution and are especially useful for studying the bar and inner disk. Each tracer is a different layer. Overlay them, and the galaxy becomes richer, but it also becomes less like the simple diagram. Even our own immediate environment illustrates the problem. The Sun is often shown sitting neatly between two major spiral arms in a minor feature called the local arm, or Orion arm. For years, this local structure was frequently treated as a small spur. More precise measurements have shown that it is substantial, containing significant star formation and extending for thousands of light years. Whether it should be described as a branch, segment, spur, or arm-like structure depends partly on how spiral structure is defined and modeled. This is not merely an argument about names. It reveals a deeper uncertainty. Spiral galaxies do not always organize themselves into a few perfectly continuous, symmetric arms. Structures can split, they can merge, they can vary by tracer, they can change with radius, they can evolve over time. And because we are embedded in the disk, a feature that looks continuous from our position may connect differently when reconstructed from above. That reconstruction depends on distances. If the distance to a group of objects shifts, the apparent geometry of the arm can shift with it. If enough anchors move, the large-scale pattern changes. So before asking how many arms the Milky Way has, or where they begin and end, there is a more basic question underneath. How certain are we that every point has been placed in the right location? The answer varies dramatically from one part of the galaxy to another. Around the Sun, the map is dense. Along carefully measured maser lines of sight, it is strongly anchored. Across heavily obscured and distant regions, it becomes thinner. And on the far side of the Milky Way, the geometry begins working against us in almost every possible way. The distance is larger. The dust column is greater. The line of sight crosses more stars and more gas. Sources overlap. Parallaxes become smaller. Optical surveys lose access to many targets. Kinematic models become more influential. The far side is not completely unknown, but it is where the idea of a finished galactic map becomes hardest to defend. Because from where we are standing, one entire half of the Milky Way must often be reconstructed through the other. If the Milky Way were a simple four-armed spiral drawn on a sheet of paper, the far side would mostly be a problem of filling in missing points. But that is not the galaxy we live in. The deeper difficulty is that astronomers are still deciding what exactly counts as a spiral arm. From outside, the problem can look almost trivial. Many spiral galaxies display long arcs of luminous young stars, dark dust, and glowing gas. Trace those arcs inward and a pattern emerges. Some galaxies have two dominant arms, others have several, some are orderly, others are fragmented into shorter pieces. For the Milky Way, that classification has to be performed from inside the disk. And depending on which population of objects is used, the answer changes. Radio measurements of high-mass star-forming regions have provided some of the strongest geometric evidence for a Milky Way, containing 4 substantial spiral arms. Precise parallaxes to masers place individual regions in 3 dimensions, allowing astronomers to fit curved arm segments across much of the disk. Those measurements are difficult to dismiss because many of the distances are geometric. But they do not mean that every component of the Milky Way follows 4 equally strong, continuous stellar arms. Infrared surveys that are especially sensitive to older stars have produced a different emphasis. In some analyses, 2 arms appear more prominent in the underlying stellar mass distribution, while gas and young stars outline additional structures. Gaia has complicated the picture further. Its stellar position and motions show spiral features that are less clean and less symmetric than the textbook image, with multiple structures in the disk rather than a single obvious grand design. These results are not necessarily contradictions. They may be describing different things. A spiral arm can be conspicuous because it contains many young, bright stars. It can be conspicuous because dense gas is producing new stars. It can be conspicuous in radio emission, but much less obvious in the older stellar population that contains most of the disk's accumulated history. The Milky Way may therefore have a spiral pattern whose appearance depends on which layer of the galaxy we choose to illuminate. This changes the meaning of the familiar question: how many arms does the Milky Way have? There may not be one number that describes every component equally well. Consider how an arm is traced. Massive blue stars are excellent markers of recent star formation because they live briefly by astronomical standards. They do not have enough time to wander across enormous fractions of the disk before they die. Where they are concentrated, something recently produced them, but they are also comparatively rare. Cold molecular gas provides another tracer because stars form inside molecular clouds. Yet clouds are clumpy, irregular, and affected by local dynamics. Masers offer extremely precise distances, but only in particular environments where suitable emission is produced. Cepheid variables provide another population with useful distance information, but they sample the disk differently. Older stars tell us where much of the long-lived stellar population resides, but they need not trace the same sharp features as newly forming stars. Each method gives astronomers points along a structure. None gives a luminous outline painted continuously across the galaxy. An arm can therefore vanish from one dataset and remain obvious in another. It can appear to end because the tracer becomes sparse. It can seem to split because two concentrations diverge. It can appear to connect with another feature because the section between them lies behind dust or lacks precise distance anchors. This is especially dangerous when diagrams turn uncertain connections into smooth curves. A continuous line is persuasive. Nature is under no obligation to draw one. The problem becomes even more interesting when we ask what a spiral arm physically is. The simplest mental image is a permanent collection of stars traveling together around the galactic center, like material painted onto a rotating wheel. That picture cannot explain the entire phenomenon. Stars throughout the disk orbit the center, but the spiral pattern does not have to behave as though each arm were a rigid object made from the same stars forever. Historically, one explanation treated spiral structure as a wave-like enhancement moving through the disk. Stars and gas could pass into and out of a region of greater density rather than remaining permanently inside one material arm. That idea helped explain how spiral patterns might persist despite differential rotation. Differential rotation is crucial because the Milky Way does not rotate like a solid plate. Objects at different distances from the galactic center have different orbital circumstances. If an arm were simply a fixed row of the same stars, ordinary orbital motion would tend to distort and wean the pattern over time. A spiral structure, therefore, has to be understood dynamically. But modern simulations and observations have made the picture more complicated than one universal long-lived density wave pattern. Spiral features can be influenced by the central bar. They can respond to gravitational interactions. They can grow, weaken, branch, and reorganize. Some spiral structure may be comparatively transient. Different parts of a disk may not share one perfectly constant pattern speed. A galaxy can look orderly in a single image while the structures producing that appearance are evolving. For the Milky Way, this creates a second kind of map. There is the spatial map, where the arms appear to be now. Then there is the dynamical map, how those structures are moving, changing, and interacting with the stars and gas around them. Gaia is especially important for the second problem because it does not merely tell astronomers where large numbers of stars are located. It tells them how stars move across the sky. Once those motions are combined with radial velocities for appropriate samples, the disk stops looking like a static arrangement of points. Patterns appear in velocity space. Groups of stars can share motions even when they are not part of a single gravitationally bound cluster. The influence of the galactic bar and spiral structure can leave signatures in stellar orbits. Past disturbances can survive as patterns in phase space long after the original event has evolved. The galaxy becomes something closer to a moving fluid of stars than a fixed architectural plan. That is a major change in perspective. A traditional map asks where everything is. A modern galactic map increasingly asks where everything is, how it is moving, how old it is, what it is made of, and what gravitational history could have produced those properties. Position alone is no longer enough. That makes spiral arms both easier and harder to understand. Easier, because motion can reveal relationships that position by itself hides. Harder, because the structures turn out not to be simple pieces of geometry. Take the local arm. From our position inside it, the local arm is unusually important because a large fraction of the nearby star-forming landscape belongs to this structure. Older diagrams often made it look like a short minor spur squeezed between larger arms. Geometric measurements of star-forming regions have shown that it is more extensive and organized than such a description suggests. But calling it an arm does not settle how it formed. It could be related dynamically to neighboring major structures. It could be a branch. It could be part of a more complicated network of segments. Its appearance depends on the population being mapped. And because we live inside it, the local arm is also a reminder that proximity can distort intuition. The feature around us receives exceptionally detailed measurements. A feature of comparable importance on the far side of the galaxy may be represented by far fewer anchors. If the map were drawn according to data density rather than inferred structure, it would look badly unbalanced. Our neighborhood would glow with precision. The far side would dissolve into isolated islands of information. That imbalance is partly being reduced. Radio interferometry can operate through regions that visible light cannot penetrate. Infrared surveys expose stars behind heavy dust. Variable stars provide distance information across large sections of the disk. Gaia supplies enormous stellar samples where optical observations remain practical. But there is no magical wavelength that removes every limitation. Radio observations can see through dust, but only certain sources provide the precise geometric anchors needed for the best distance measurements. Infrared light penetrates dust more effectively, but extinction does not disappear completely, and crowding toward the inner galaxy remains severe. Optical astrometry can be exquisitely precise, yet the galaxy itself blocks many optical targets. Every solution opens another trade-off, and then there is the central bar. The Milky Way is not simply a spiral disk wrapped around a round center. Its interstellar distribution contains a bar, an elongated concentration of stars extending through the central region. From our location, we see that bar at an angle and through some of the most crowded, dust-obscured lines of sight in the sky. Determining its orientation, length, shape, and relationship to surrounding spiral structure requires combining stellar counts, infrared observations, distances, motions, and dynamical models. Even the center of the textbook diagram is therefore a reconstruction. That matters because the bar is not merely decorative. Its gravity can rearrange stellar orbits and gas flows. It may help shape where spiral features connect to the inner galaxy. Gas moving through a barred gravitational potential does not necessarily follow simple circular paths. And once those non-circular motions enter the problem, using velocity as a shortcut to distance becomes more difficult precisely where the structure is most crowded. The map and the dynamics begin to depend on one another. To determine where material is, astronomers may need a model of how it moves. To determine how the galaxy moves, they need reliable distances to the material. The solution comes from combining independent methods until only a narrower range of structures remains consistent with all of them. This is how the Milky Way has slowly acquired its recognizable form, not by being photographed, not by one perfect survey, not by drawing curves through bright patches on the sky. It is reconstructed through agreement between different kinds of evidence. And where those methods disagree, the disagreement is useful. It tells astronomers where the simple picture has failed. The spiral arms are one example. But the largest hidden structure in the Milky Way is not an arm at all. It surrounds every arm, every star, every gas cloud, and the central bar itself. We cannot see it directly. Yet without it, the galaxy would not move the way it does. To finish even a gravitational map of the Milky Way, astronomers have to chart something that emits no light. The invisible part of the Milky Way does not appear on any photograph. It appears in motion. Watch a star orbit the galactic center, and gravity is already telling us something about the mass around it. Measure enough stars at enough distances, add the motions of gas and satellite systems, and the galaxy begins to reveal a structure that light alone cannot trace. This is where mapping the Milky Way changes from astronomy into gravitational archaeology. The bright disk is only part of the mass distribution controlling the motion of the galaxy. There are stars, there is gas, there is dust, there is the central bulge and bar, and then there is a much larger component that does not emit, absorb, or reflect enough electromagnetic radiation to be mapped in the ordinary way. Dark matter. The name can make it sound as though astronomers have already located a hidden substance and are simply waiting to identify what it is made of. The actual situation is more careful. What is directly measured is gravity. Across galaxies, galaxy clusters, gravitational lenses, large-scale structure, and the cosmic microwave background, the evidence indicates that ordinary visible matter is not enough to explain the gravitational behavior of the universe under the standard cosmological model. Inside the Milky Way, the same problem becomes local. If astronomers can determine how stars and gas move at different distances from the galactic center, they can ask how much gravitational mass must be to produce those motions. The result is a mass map, but it is not a direct image of dark matter particles. It is an inference from dynamics. One of the classic tools is the galactic rotation curve. Imagine measuring the orbital speed of material at different radii from the center. If nearly all of the galaxy's mass were concentrated toward the bright inner regions, then far outside that concentration, orbital speeds would be expected to decline in a roughly Keplerian way. The farther an object moved from the dominant mass, the slower its orbit should become. Galaxies generally do not behave that simply. Historically, observations showed that orbital speeds across large portions of many spiral galaxies remain higher than the visible mass alone would suggest. That was one of the major lines of evidence for extended dark matter halos. The Milky Way should offer an unusually detailed test, because we can measure the motions of individual stars. But once again, our position inside the galaxy complicates what sounds like a straightforward experiment. To construct a rotation curve, astronomers need distances. They need velocities. They need the motion of the sun relative to the galaxy. They need the distance from the sun to the galactic center. They need to account for the fact that many stars are not moving on perfect circles. The bar perturbs orbits. Spiral structure perturbs orbits. Stars move above and below the disk. Groups can retain signatures of old disturbances, and the farther outward the measurements extend, the more sparse and uncertain the tracers can become. Gaia has transformed this problem by providing astrometry and motion measurements on a scale that previous surveys could not approach. Analyses using Gaia data have now traced the Milky Way's rotation far beyond the immediate solar neighborhood. Some recent studies have found evidence that the rotation curve declines in the outer disk rather than remaining perfectly flat. That result matters. But it does not mean dark matter has disappeared. Nor does one measured decline uniquely determine the shape or total mass of the dark halo. Different analyses make different assumptions about the stellar populations being used, the equilibrium of the disk, the distribution of ordinary matter, the shape of the halo, and the conversion from observed velocities into the underlying gravitational potential. Those assumptions can change the inferred mass substantially. This is a recurring lesson in galactic mapping. The observations can become extraordinarily precise, while the interpretation remains model-dependent. Dark matter makes that distinction unavoidable. Suppose a star is moving faster than the visible matter appears able to explain. That is an observation about motion. To infer the dark matter distribution, astronomers must first subtract the gravitational contribution of everything they can see. And that visible contribution is not known perfectly. How much mass is in the stellar disk? How does that mass change with distance from the center? How much gas is present? How thick is the disk? What is the mass of the bulge? What is the exact structure of the central bar? Even ordinary matter becomes part of the uncertainty in the dark map. The trade-off is almost paradoxical. To map the invisible galaxy, we first need an accurate map of the visible one. Then the gravitational influence that remains can be attributed, within the standard framework, to the unseen halo. The halo itself is thought to extend far beyond the bright stellar disk. That changes the scale of the Milky Way completely. In a visible light image, the galaxy seems to end where the stars become too sparse to define the disk. Gravitationally, there is no comparable sharp edge. The region controlled by the Milky Way stretches outward through a diffuse stellar halo, globular clusters, satellite galaxies, gas, and a dark matter distribution whose outer boundary cannot be drawn as a clean line. The Milky Way is therefore larger in one sense than the familiar spiral picture suggests, but even saying how massive it is becomes difficult. To weigh the inner galaxy, astronomers can use enormous numbers of stars. To weigh the far outer halo, they have far fewer tracers. That shifts attention to objects that would look insignificant on an ordinary galactic diagram. Globular clusters, distant halo stars, dwarf galaxies, and stellar streams. Stellar streams are among the most revealing. A globular cluster or small satellite galaxy can be gradually torn apart by the Milky Way's tidal field. Its stars do not immediately scatter randomly through space. They can stretch into long, thin streams that follow related orbits around the galaxy. Those streams behave like test particles distributed across enormous distances. Their shapes and motions respond to the gravitational potential they travel through. If the Milky Way's halo were perfectly spherical, a stream would evolve one way. If the halo were flattened, elongated, lopsided, or being perturbed by another massive object, the stream could follow a different path. So a faint ribbon of stars becomes a probe of invisible structure. But this method introduces another complication. The Milky Way is not an isolated gravitational system. Its satellite galaxies exert forces of their own. The most important example is the Large Magellanic Cloud. For a long time, diagrams could make it look like a small companion orbiting a vastly dominant Milky Way. Dynamically, that description is incomplete. The Large Magellanic Cloud is massive enough that its gravitational influence can disturb the outer halo, alter stellar orbits, affect streams, and even shift the Milky Way's own motion around the combined system's changing center of mass. This means a stream can be distorted not only by the shape of the Milky Way's dark matter halo, but also by a large satellite moving through it. Ignore that interaction, and the inferred halo shape can be wrong. Include it, and another uncertain quantity enters the reconstruction: the mass and orbital history of the Large Magellanic Cloud itself. Again, the map becomes a coupled problem. We want the stream to tell us the galactic potential, but to understand the stream, we need to know the perturbations acting on it. We want satellite motions to tell us the Milky Way's mass. But those satellites have their own histories and may not trace a perfectly relaxed population. The farther outward we move, the more the galaxy begins to look less like a static object, and more like a system still responding to its environment. That includes evidence of past collisions. Gaia's stellar motions have helped expose structures left by ancient merger events. Some groups of halo stars occupy distinctive patterns of motion and chemistry consistent with stars that formed in smaller galaxies before those systems were incorporated into the Milky Way. These remnants do not simply tell us where matter is. They reveal how the galaxy was assembled. The map gains a time dimension. A star's current position may say relatively little about where it formed. Its chemical composition can preserve information about its birthplace. Its orbit can preserve information about a merger. A stream can preserve the destruction of a cluster or dwarf galaxy. A warped disk can preserve gravitational disturbance. The present-day Milky Way is therefore filled with incomplete records of previous versions of itself. Dark matter adds another unresolved layer to that history. Under the standard cosmological picture, the galaxy formed and evolved inside a dark matter halo that provided much of the gravitational framework into which ordinary matter collected. But the precise shape of that halo remains difficult to determine. Is it close to spherical across the regions we can probe? Is it flattened? Does its shape change with radius? How much has the Large Magellanic Cloud distorted it? How smoothly is the dark matter distributed? How much substructure survives from smaller halos incorporated during the galaxy's formation? Different tracers can favor different answers because they probe different regions and depend on different assumptions. There is also a more local version of the problem. Dark matter, if the standard model is correct, should pass through the region containing the solar system. Direct detection experiments on Earth are designed around assumptions about the local dark matter density and velocity distribution. Galactic cartography, therefore, reaches all the way into laboratories beneath Earth's surface. To predict how often a hypothetical dark matter particle might interact with a detector, physicists need some idea of how much dark matter should be moving through our neighborhood and how fast it should be moving. Those quantities are inferred partly from the dynamics of nearby stars. A measurement of stellar motion thousands of light years across the disk can ultimately influence the interpretation of an experiment conducted inside a tank or crystal on Earth. The map is no longer merely descriptive. It becomes part of the search for new physics, and yet no direct detection has established what the dark matter of the Milky Way is made of. The gravitational evidence can constrain where unseen mass must be. It cannot by itself tell us the particle identity behind that mass. That leaves the largest structure in the galaxy as one of the least directly visible. We can map its influence. We can test models of its shape. We can watch streams respond to its gravity. We can measure stars accelerated within its potential. But the halo remains a reconstruction surrounding another reconstruction. And even that is not the outer limit of the problem. Because the stars far above and below the Milky Way's bright disk contain evidence that the galaxy has repeatedly swallowed smaller systems. To understand the shape we see today, we have to recover a history in which the Milky Way was never finished at all. The Milky Way did not form in one piece. That sounds obvious in modern cosmology, but it changes what a map of the galaxy is supposed to represent. A map drawn only from present-day positions suggests a finished object: disk, bar, spiral structure, halo. The real Milky Way is the surviving result of construction, disruption, accretion, orbital mixing, and repeated gravitational encounters. Some of the stars around us were born inside the galaxy. Others were born in smaller galaxies that no longer exist as independent systems. Some belong to structures that have been stretched so completely around the Milky Way that their original shape has nearly disappeared. A modern galactic map, therefore, has to answer more than where stars are. It has to ask where they came from. That question cannot usually be answered by position alone. A star captured billions of years ago may now pass through the same region of space as a star formed inside the Milky Way. Their current locations can overlap completely. Their histories may be different. Astronomers look for that history in two places: motion and chemistry. Stars preserve chemical information from the gas clouds in which they formed. Their atmospheres contain measurable abundances of elements produced by earlier generations of stars: iron, magnesium, silicon, calcium, carbon, nitrogen, and many others. The relative abundances matter because different enrichment processes operate on different timescales. Massive stars live briefly and enrich their surroundings quickly through supernova explosions. Other sources return different elements over much longer periods. A galaxy's history of star formation therefore influences the chemical patterns recorded in later generations of stars. Two populations occupying the same part of the Milky Way today can carry different chemical histories. That makes stellar chemistry a kind of archival record, not a perfect birth certificate, but evidence. Combine chemistry with motion, and disrupted structures become easier to recognize. This approach is often called galactic archaeology. The name is appropriate because the original systems are usually gone. Astronomers are reconstructing them from remnants. One of the most important discoveries of the Gaia era was not a new object in the sky. It was a pattern in the motions of stars that had already been there. Large numbers of nearby halo stars were found to occupy unusual, strongly elongated orbits. Their chemical properties also differed from populations thought to have formed within the early Milky Way. The broad interpretation is that many of these stars came from a substantial ancient galaxy that merged with the Milky Way billions of years ago. That event is often associated with names such as Gaia Enceladus or Gaia Sausage Enceladus, reflecting different analyses of the same broad accreted population. The exact reconstruction remains an active research problem. The original galaxy cannot be photographed. Its shape is gone. Its stars have been redistributed across the Milky Way. What remains is a dynamical and chemical fingerprint. This is a completely different kind of map. Instead of drawing a border around a satellite galaxy, astronomers identify a population spread through phase space. A destroyed galaxy can survive as a statistical structure. And once that possibility became clear, the Milky Way's halo stopped looking like a random collection of old stars. It began to look layered. Different groups may record different accretion events. Some are comparatively easy to recognize because they remain in coherent streams. Others are so thoroughly mixed that only their orbital properties and chemistry separate them from the rest of the halo. The distinction depends partly on time. A recently disrupted satellite can leave a narrow stream. An ancient merger has had billions of years for its stars to move around the galaxy. Their positions disperse. Their orbital signatures can persist longer. Their chemical patterns may persist longer still. This means the age of an event determines what kind of evidence remains available. The Sagittarius dwarf galaxy offers a vivid example at the less completely mixed end of the process. It is being tidally disrupted by the Milky Way. Stars stripped from it have formed enormous streams extending across the sky. From Earth, those stars do not appear as one dramatic ribbon visible to the naked eye. They have to be identified through surveys, distances, velocities, and population properties. Once reconstructed, the Sagittarius stream wraps around the galaxy over vast distances. Its geometry records repeated passages through the Milky Way's gravitational field. That makes it useful for studying the galactic potential. But it also complicates the map. The stream is not a simple orbit drawn in an unchanging gravitational field. The Milky Way evolves. The Sagittarius system loses mass as it is disrupted. The Large Magellanic Cloud exerts additional gravitational influence. The dark halo may not be perfectly spherical. Every one of these effects can alter the trajectory. A stellar stream is therefore both evidence and experiment. It tells us about the past only after we have modeled the forces acting on it. Again, reconstruction depends on dynamics, and the disruption of smaller galaxies does not only populate the halo, it can influence the disk. A thin stellar disk is gravitationally delicate. Perturb it, and stars can be pushed into vertical oscillations or redistributed in orbital energy and angular momentum. The Milky Way's disk is not perfectly flat or perfectly symmetric. Its outer regions are warped. They also contain vertical structure and asymmetries that cannot be understood by imagining the disk as an undisturbed plane. Some of those features may be related to interactions with satellite galaxies. The exact contributions of different perturbers are still being investigated. Sagittarius has often been considered important. The Large Magellanic Cloud is increasingly recognized as dynamically significant. Internal structures such as the bar and spiral pattern can also generate complex motions. The problem is difficult because several mechanisms can produce overlapping signatures. A ripple in stellar motion does not automatically identify the object that caused it. The same observed structure may have multiple possible origins. This is where Gaia provided another major change in perspective. When astronomers examined stellar motion in the solar neighborhood with unprecedented precision, the vertical positions and velocities of stars did not form the smooth distribution expected from a perfectly settled disk. Instead, they revealed a spiral-like pattern in phase space. The pattern is not a physical spiral arm in ordinary space. It emerges when stellar height above the galactic plane is plotted against vertical velocity. Its existence suggests that the disk has been disturbed and is still dynamically responding. It is sometimes called the phase space spiral. The shape contains information about the disturbance and the galactic gravitational potential. But identifying a unique cause is more difficult. An interaction with Sagittarius is one leading possibility considered in many studies. Internal evolution can also contribute. The important point is not that one satellite definitely produced one pattern. It is that the disk has memory. A gravitational encounter can end, while the response remains measurable much later. So the Milky Way contains several different clocks. Stellar ages record when stars formed. Chemical abundances record enrichment histories. Streams record disruption. Orbital patterns record perturbations. The disk itself can retain waves from past events. Mapping the galaxy means learning to read those clocks together. That also changes how we think about the halo. A traditional diagram shows a bright disk inside a faint spherical envelope. But the stellar halo is not simply a smooth cloud. It contains remnants, streams, shells, chemically distinct populations, globular clusters, and stars on extreme orbits. Some of those structures formed within the Milky Way. Others were imported. Some may trace systems that merged so early that their identity can only be recovered statistically. There is no obvious line on the sky separating native from accreted stars. The distinction emerges from data. That is why large spectroscopic surveys have become essential companions to astrometric missions. Gaia gives extraordinarily powerful information about positions and motions. Spectroscopy adds radial velocities, stellar parameters, and chemical composition for selected populations. Combine the two, and astronomers can move from a geometric map toward a historical one. A star becomes more than a point. It becomes a trajectory, a composition, an approximate age, a possible origin. Enough stars can reveal a population. Enough populations can reveal an event. And enough events can begin to reconstruct the assembly of the galaxy. But there is a limit. The farther back in time we go, the more thoroughly structures become mixed. Orbits change. The galactic potential changes. The bar grows and evolves. Spiral structure redistributes angular momentum. Satellite interactions perturb trajectories. Stars migrate away from their birth radii. A present-day orbit cannot simply be integrated backward for 10 billion years, as though the Milky Way were a perfectly known, unchanging machine. The uncertainty expands backward. This means galactic archaeology can identify major pieces of history without recovering every detail. It may reveal that a population was accreted. It may constrain when a merger occurred. It may estimate the original system's mass. But reconstructing the exact geometry of the encounter becomes progressively harder as time passes. The evidence survives, the original scene does not. This is one reason the phrase map of the Milky Way is becoming almost inadequate. There is a map of where the stars are, a map of how they move, a map of their chemical composition, a map of the gas, a map of the dust, a map of the gravitational field, a map of stellar ages. And beneath all of them, an attempted reconstruction of how those layers were assembled. The Milky Way we observe today is only the latest frame. Its current shape is temporary. Satellite galaxies are still orbiting. Streams are still forming. The disk is still responding. Stars are still migrating. The bar and spiral structures are still evolving. The halo is still being perturbed. Even if astronomers could determine the position of every star tomorrow, the map would immediately begin to become outdated. And there is another reason completeness remains impossible. Some stars are not merely difficult to classify, they are difficult to see at all. The galaxy contains regions where dust, crowding, brightness limits, and stellar confusion overwhelm even the surveys that have transformed our view of the Milky Way. To understand how much of the map is still missing, we have to move into the places where billions of stars become an observational obstacle rather than an advantage. The Milky Way becomes hardest to map where it contains the most information. Toward the galactic plane, stars overlap in enormous numbers. Dust clouds absorb visible light. Bright foreground objects sit in front of faint distant ones. Multiple structures fall along the same line of sight. A telescope does not receive a neat sequence arranged by distance. It receives everything at once. This is the crowding problem. If two stars are separated widely enough on the sky, a telescope records two distinct points. Bring them closer together, and their images begin to overlap. At some point, especially in dense fields, the instrument can no longer separate them cleanly. The light from several stars blends into what may look like a single source or a distorted measurement. The problem depends on angular resolution, wavelength, brightness, detector performance, and the density of the field. Near the galactic poles, where we look away from the thin disk, crowding can be modest. Toward the inner Milky Way, it becomes severe. The galactic center is an extreme case. There, a relatively small patch of sky contains huge numbers of stars projected on top of one another. Dust blocks visible light so heavily that optical astronomy is restricted to a fraction of what is actually present. Infrared observations reveal far more, but better penetration through dust does not automatically separate every star from its neighbors. The map becomes confusion limited. That phrase captures a fundamental distinction. Sometimes a telescope fails to detect an object because the object is too faint. Sometimes it fails because too many other objects are present. Build a more sensitive detector, and the first problem improves. For the second, greater sensitivity can actually reveal even more overlapping sources. Resolution becomes the controlling limit. This is why different observatories can produce radically different maps of the same region. A wide field survey may record millions of stars efficiently, but struggle in the most crowded areas. A telescope with finer angular resolution can separate sources that the wider survey blends together, but it may cover much less sky at a time. Ground-based telescopes can use adaptive optics to correct for much of the blurring introduced by Earth's atmosphere, allowing extremely sharp infrared measurements in small regions. Space telescopes avoid atmospheric turbulence entirely. Each system trades field of view, wavelength access, sensitivity, resolution, cadence, and observing time against the others. There is no single instrument that optimizes every requirement simultaneously. Gaia illustrates the trade-off clearly. Its great strength was repeated precision measurement across essentially the entire sky. That design allowed it to determine parallaxes and motions for an immense stellar sample. But the densest regions of the Milky Way are among the most difficult environments for the mission's measurements. When many sources pass through the focal plane close together, distinguishing and processing them becomes harder. Dust adds another bias by removing optically faint or extinguished stars before they can be measured well at all. So the survey that revolutionized our three-dimensional map also leaves some of the most structurally important regions less completely sampled than the relatively transparent neighborhood around the sun. That imbalance matters. The inner galaxy contains the central bar. It contains the transition between the bar and the spiral structure. It contains intense star formation, dense molecular gas, and stellar populations spanning much of the history of the Milky Way. It is exactly the region we would most like to reconstruct cleanly, and it is exactly the region where geometry, extinction, and crowding work together against us. Infrared astronomy helps because dust is less effective at blocking longer wavelengths, but the word less is important. Infrared does not make the entire galaxy transparent. Dense clouds can remain highly opaque even at wavelengths much longer than visible light. The amount of extinction also depends on wavelength and on the properties of dust grains along the line of sight. To determine how bright a star would appear without dust, astronomers need an extinction law describing how the intervening material modifies its light. If that law is slightly wrong, the inferred luminosity can shift. If luminosity shifts, a photometric distance can shift. If thousands of stellar distances shift together, the apparent shape of a galactic structure can shift with them. Dust, therefore, does not simply hide parts of the map. It can distort the coordinates of objects that remain visible. This is one reason three-dimensional dust maps have become essential. Rather than treating extinction as a single screen between Earth and the entire galaxy, astronomers try to determine how dust accumulates with distance along individual lines of sight. Nearby stars with known or estimated distances serve as probes. If a group of stars becomes progressively redder beyond a certain distance, a dust cloud may lie there. Repeat that process across the sky, and the obscuring material itself becomes a three-dimensional structure. But the reconstruction is uneven. Where many well-measured stars are available, the dust can be mapped in detail. Where stars disappear behind dense clouds, the very material being mapped removes the background sources needed to measure it. The darkest clouds can hide their own far sides. Gas provides another way into the obscured galaxy. Neutral atomic hydrogen emits radio radiation at a characteristic wavelength near 21 centimeters. Because radio waves pass through interstellar dust far more easily than visible light, surveys of this emission reveal gas across enormous regions of the galactic disk. For decades, hydrogen maps have been central to attempts to trace large-scale galactic structure. But once again, seeing the gas does not automatically tell us where it is. A radio spectrum can provide velocity along the line of sight. Turning that velocity into distance often requires a model of galactic rotation. And the farther the actual gas motion departs from ideal circular rotation, the less reliable the conversion becomes. Molecular gas presents similar opportunities and limitations. Carbon monoxide emission is commonly used to trace molecular clouds because cold molecular hydrogen, although dominant in those clouds, is difficult to observe directly under typical conditions. CO surveys can reveal major concentrations of star-forming material through the disk. Yet converting emission intensity into molecular mass requires assumptions. Assigning distances can require additional assumptions. Cloud boundaries can overlap in position and velocity. A beautifully detailed radio map may therefore still be ambiguous in three-dimensional space. This is a recurring theme across almost every galactic survey. A two-dimensional measurement can be precise. The third dimension is expensive. Even source identification can become difficult. Suppose an infrared survey detects a star behind heavy dust. A radio survey detects a compact maser in roughly the same direction. An X-ray telescope sees an energetic source nearby. Are all three measurements coming from the same physical system? Or do three unrelated objects happen to overlap from Earth's perspective? Cross-matching catalogs sounds like bookkeeping. In crowded regions, it becomes part of the science. Positions have uncertainties. Different instruments have different resolutions. Sources can vary in brightness. Some move measurably over time. A source visible in one wavelength may have no obvious counterpart in another. Before astronomers can combine datasets into a richer map, they must determine which detections belong together. The denser the field, the harder that becomes. The far side of the galaxy adds distance to every one of these problems. From the Sun, a line of sight toward a distant spiral feature may cross local dust, nearby stars, several gas clouds, an inner spiral structure, the central region, and additional material beyond it before reaching the target. Every foreground layer can alter what arrives. Some wavelengths survive, some do not. Some objects blend, some vanish, and the target itself may be faint simply because of distance. That means the far side is not missing for one reason. It is missing through accumulated observational penalties. This is why rare geometric distance measurements on the far side are so valuable. Radio masers can sometimes be observed through the dusty disk and measured with very long baseline interferometry. When a parallax is obtained for one of these distance-forming regions, it provides an anchor that does not depend on converting galactic rotation into distance. Each new anchor can test whether a presumed spiral feature lies where models placed it. But the number of such measurements remains tiny compared with the number of stars and clouds that make up the galaxy. The final picture therefore combines strong anchors with broad statistical structure. It is a little like constructing a coastline from a few surveyed landmarks and many less certain observations between them. Except the Milky Way has no fixed coastline. Its spiral features move. Its disk warps. Its gas responds to gravitational forces. Its stars migrate. And some of the foreground material used to interpret the map is changing too. The outer disk introduces another difficulty. Crowding generally decreases as stellar density falls. Dust can become less severe in many directions. But now the problem is faintness. Stars become sparse. Young tracers become less common. Distances grow. The disk bends away from a simple plane. The structures being mapped become more diffuse. The observing challenge changes, but it does not disappear. Near the center, too many sources can hide the map. Far from the center, too few usable sources can weaken it. This is why completeness is not simply a matter of building a more powerful telescope. A larger telescope can detect fainter stars. Higher resolution can separate crowded ones. Infrared wavelengths can penetrate more dust. Radio arrays can provide geometric distances to selected sources. Large surveys can map motions across billions of objects. But every technique samples a particular population under particular conditions. The missing regions move as the method changes. What optical astrometry cannot see, infrared may recover. What infrared cannot place precisely in depth, radio parallax may anchor. What stellar surveys miss, gas surveys may reveal. What gas velocities cannot locate uniquely, stellar distances may constrain. The map improves by overlap. Its strength comes from independent methods agreeing where they can, and its uncertainty becomes most visible where those methods stop overlapping. This creates a useful way to think about the Milky Way, not as one picture with holes, as a stack of partially transparent maps, one for stars, one for dust, one for atomic gas, one for molecular clouds, one for velocities, one for stellar ages, one for chemistry, one for the gravitational field. Where many layers coincide, the galaxy becomes sharply defined. Where only one or two remain, the picture becomes provisional. And there is one structure that makes this layered approach unavoidable. The Milky Way's disk itself is not flat. Far from the center, it bends, it ripples, it flares. And once astronomers began measuring those departures in detail, another familiar element of the textbook galaxy had to be abandoned. The clean, level spiral disk was never the whole shape. The Milky Way is usually drawn as a thin disk because, compared with its diameter, most of its stars are concentrated near a relatively narrow plane. But thin does not mean flat. Move far enough from the galactic center, and the disk begins to bend. One side rises above the plane defined by the inner galaxy. The opposite side bends below it. This distortion is called the galactic warp. It has been known for decades, first becoming clear through observations of gas, and later through increasingly detailed stellar surveys. In a textbook illustration, the warp can look like a cosmetic imperfection added to an otherwise stable disk. It is not. The warp is evidence that the outer Milky Way is dynamically disturbed. And once astronomers began measuring not only where warped stars are located, but how they are moving, the distortion became harder to explain as a fixed shape. The warp appears to evolve. Gaia measurements have shown that its orientation changes with time, a motion often described as precession. That means the outer disk is not simply bent into a permanent configuration. It is moving while it is bent. The distinction is critical. A static warp might be produced by one set of long-lived gravitational conditions. A moving warp can constrain the forces acting on the disk much more strongly. Several mechanisms have been proposed. The dark matter halo surrounding the Milky Way may not be perfectly aligned with the stellar disk. The Large Magellanic Cloud can gravitationally disturb the galaxy. The Sagittarius dwarf galaxy has repeatedly interacted with the Milky Way and may have driven waves through the disk. Gas accreting onto the galaxy could also contribute under some models. The observed warp does not yet provide a single uncontested answer. What it provides is a moving target that every explanation has to reproduce. Its shape, its amplitude, its dependence on radius, its behavior in different stellar populations, and its motion through time. That last requirement is especially demanding because different stars do not all trace the warp in exactly the same way. Young populations can respond differently from old ones. Gas can emphasize structures that are weaker in stars. A measurement using Cepheid variables may describe a somewhat different disk from one based on older giants. Even the line around which the disk changes from bending upward to bending downward can vary with radius rather than remaining a perfectly straight axis. The Milky Way's outer disk is not behaving like a rigid sheet. It behaves more like a layered, gravitationally responsive structure. And the warp is only one departure from flatness. The disk also flares. Closer to the galactic center, stars are concentrated relatively tightly around the midplane. Farther outward, the vertical thickness of some stellar populations increases. The disk spreads out. From the side, instead of maintaining the same thickness all the way to its edge, the stellar distribution becomes broader. This is the galactic flare. Warp and flare are different effects. A warp moves the average midplane upward or downward. A flare increases the vertical spread around that midplane. A disk can do both at once. That matters for mapping because an astronomer who assumes a flat disk with constant thickness can misinterpret stars that appear far above or below the expected plane. They may not be unusual halo stars at all. They may belong to the outer disk itself. The boundary between disk and halo becomes less visually obvious. And the farther outward astronomers look, the more the galaxy resists the clean categories used in simple diagrams. Thin disk, thick disk, outer disk, stellar halo. These are useful descriptions. They are not walls. Stellar populations overlap. Their relative importance changes with radius and height. Different methods divide them differently. A star does not encounter a physical surface when it moves from one component to another. The components emerge statistically from distributions of position, motion, age, and chemistry. The flare makes this especially clear. If the disk thickens with radius, then a cut based only on height above the galactic plane will select different populations at different locations. A definition that works near the Sun may fail farther out. Once again, the map depends on the model used to interpret it. Then Gaia revealed something even more difficult to fit into a static picture. Across a large portion of the outer disk, stars show evidence of a broad vertical wave. This is not simply the known warp. The warp describes a large-scale bending of the disk. The newer structure appears as a corrugation superimposed on that larger shape. In some regions, stars lie above the warped midplane, in others below it. Their vertical motions also show a systematic pattern consistent with stars participating in a wave-like disturbance. The feature extends across tens of thousands of light-years. It was identified using young giant stars and Cepheid variables, populations that can be traced over large distances. The importance is not the visual drama of a ripple crossing the galaxy. The important point is that position and velocity tell the same story. If astronomers had only found alternating regions above and below the disk, those structures might have several geometric explanations. But when the star's vertical motions shift systematically relative to their vertical positions, the pattern begins to behave like something propagating through the disk. The outer Milky Way is not only warped, parts of it appear to be waving. What created that wave remains uncertain. A past interaction with a dwarf galaxy is one possibility. The Sagittarius dwarf galaxy is an obvious candidate because it has passed through the galactic disk during its ongoing disruption. But identifying one specific encounter as the cause requires more than noting that an interaction occurred. A successful model has to reproduce the location of the wave, its scale, its direction of motion, its amplitude, its relationship to stars of different ages, and the other disturbances already present in the disk. The Large Magellanic Cloud complicates the system further because its gravitational influence cannot be treated as negligible. The Milky Way's own bar and spiral structure can also generate non-circular and vertical motions. Several effects may be operating simultaneously. This is why a ripple is not a historical label. It is a constraint. The galaxy remembers gravitational disturbances, but memory does not come with a caption identifying the source. Astronomers have to reconstruct the event from the surviving response. There is a useful comparison much closer to the Sun. The solar neighborhood is associated with another large structure called the Radcliffe wave, a long coherent arrangement of nearby molecular clouds and star-forming regions. Its scale is much smaller than the newly identified outer disk wave, and the two occupy different parts of the galaxy. Whether they are related is not established. They demonstrate, however, how misleading the word plane can become. On sufficiently detailed maps, even nearby star-forming material is not distributed along one perfectly smooth galactic surface. It bends and oscillates. Zoom out and larger vertical structures appear. Zoom farther out and the warp dominates. The form of the Milky Way depends on the scale at which it is examined. This presents an unusual mapping problem. Suppose an astronomer wants to produce a face-on map of the disk. Every star must first be assigned a distance. Then its position has to be transformed relative to the galactic center. If the disk were perfectly flat, the vertical coordinate might be treated as a secondary detail. But it is not flat. To reconstruct the real geometry, the map needs 3 dimensions. Then velocity, because the warp moves, and age, because younger and older populations can respond differently, and chemistry, because populations with different origins can occupy the same region. A 2-dimensional spiral drawing is not wrong because it simplifies these things. It is wrong only if we forget that it is a projection of something much richer. The outer disk also forces astronomers to confront the idea of an edge. Where does the Milky Way's stellar disk end? There is no single sharp boundary where stars suddenly stop. The density declines. Different populations can extend to different radii. The warped and flared disk becomes increasingly difficult to separate from other sparse structures. Stars attributed to the disk may be detected at unexpectedly large distances from the center, but assigning them correctly requires good distances, good motions, and careful treatment of contamination from halo populations. Gas can extend differently from stars. Young stellar populations may trace regions where star formation still occurs. Old stars preserve earlier stages of disk growth. A map, therefore, needs another qualifier. Which Milky Way are we mapping? The present gas disk? The young stellar disk? The old stellar disk? The mass distribution? The region dynamically controlled by the galaxy? Those boundaries do not coincide. This is why the familiar diameter quoted for the Milky Way should never be mistaken for a hard physical wall. The galaxy fades outward through several overlapping components. The farther from the bright inner disk we go, the more the concept of an edge becomes dependent on what is being measured. And this returns us to the original problem. We live inside a structure whose shape is changing while we measure it. Its spiral features evolve. Its bar rotates. Its outer disk bends. The warp precesses. The disk flares. Large-scale waves move through stellar populations. Satellite galaxies perturb the system. Streams from older mergers cross the halo. The map is not only incomplete because our telescopes cannot see everything. It is incomplete because there is no permanently frozen Milky Way waiting to be recorded. Every measurement is a timestamp. Gaia has made that fact impossible to ignore. Its greatest contribution was never simply that it measured an enormous number of stars. It measured enough of their motions to turn the galaxy from a picture into a dynamical system. And that raises the next problem. If the Milky Way is moving everywhere, then a map of positions alone tells us where the galaxy is. To understand what the galaxy is becoming, astronomers have to predict where those stars are going. A map becomes far more demanding when it has to predict the future. If astronomers knew the exact position of every star in the Milky Way at one instant, they still would not possess a complete description of the galaxy. They would have a snapshot. To understand the system, they also need velocity. A star moving through the solar neighborhood may look unremarkable in position alone. Add its motion across the sky, its speed toward or away from us, and its distance, and the same star becomes part of an orbit. Do that for millions of stars, and the Milky Way gains another dimension. Not just where things are, where they are going. In principle, this sounds like the final step. Measure positions and velocities, calculate the gravitational field, and run the system forward. But galaxies are not clockwork machines in the simple sense. The gravitational potential itself evolves. The central bar rotates. Spiral structures change. Satellite galaxies move. The Large Magellanic Cloud perturbs the outer system. Sagittarius continues to be disrupted. Stars exchange angular momentum with large-scale structures in the disk. Gas cools, collapses, forms stars, and is expelled or rearranged by stellar feedback. The Milky Way of the future will not be generated merely by allowing the present stars to continue along fixed tracks. The tracks change too. That is why stellar orbits are useful without necessarily being permanent. For a short enough period, an orbit calculated in a reasonable model can reveal how a star moves through the galaxy. Over much longer periods, uncertainty accumulates. A small error in distance changes velocity. A small error in velocity changes the inferred orbit. An uncertain gravitational potential changes it again. If the potential itself evolves, integrating backward or forward under a fixed model eventually stops representing the real history. This is especially important when astronomers try to use present motion to reconstruct ancient events. The temptation is straightforward. Measure a star today, calculate its velocity, run its orbit backward several billion years, find where it came from. For an individual star, that procedure usually cannot recover a unique birthplace over the full history of the disk. Too much has happened. The galaxy has evolved. The star may have interacted gravitationally with spiral structure or the bar. Its orbit may have migrated. The potential it traveled through was not identical to the one we measure today. The information has been partially mixed away. So, galactic archaeology rarely depends on rewinding one star like a video. It works statistically. Large populations can retain patterns that individual trajectories no longer preserve cleanly. That is one reason phase space matters. For each star, 3 coordinates describe position, 3 more describe velocity. Together, those 6 quantities define a point in 6-dimensional phase space. The phrase sounds abstract, but the idea is simple. 2 stars can occupy nearly the same place while moving in completely different ways. Once velocity is included, they separate. A population that looks mixed in ordinary space can become recognizable in phase space. This is how some accreted structures emerge. It is also how resonances, moving groups, and disturbances in the disk become visible. The galaxy can hide organization in motion. Gaia made that organization accessible on an unprecedented scale because its repeated measurements were designed not merely to locate sources, but to detect their apparent motion across the sky. For appropriate stars, spectroscopy adds the missing line of sight velocity. The result is not complete, 6-dimensional information for every source. No existing survey provides perfect position and velocity measurements for every star in the Milky Way. But the available samples are large enough to reveal structures that were effectively invisible when astronomers had only positions. Some of those structures are local. In the solar neighborhood, stars do not occupy velocity space as one smooth, featureless population. They form ridges, arches, moving groups, and other patterns. Historically, some moving groups were assumed to be remnants of stars born together. That explanation works for genuine clusters and associations. But several broad velocity structures contain stars with different ages and chemical compositions. They cannot all be surviving families from one birth cloud. Instead, at least the organization is dynamical. The rotating bar and spiral structure can alter stellar orbits through resonances. A resonance occurs when characteristic orbital frequencies fall into particular relationships with a rotating gravitational pattern. The effect can concentrate or redistribute stars in velocity space even if those stars formed in different places. This means a pattern measured near the Sun can carry information about a structure thousands of light years away. The central bar can leave fingerprints in local stellar motion. That is an extraordinary inversion of ordinary mapping. Instead of looking directly at the bar to determine all of its properties, astronomers can examine how its gravity has reorganized orbits elsewhere in the disk. But this method also creates ambiguity. The bar is not the only structure capable of producing patterns. Spiral arms can perturb stars. Past satellite encounters can disturb the disks. Several processes can overlap. A feature in velocity space does not arrive labeled with its cause. Researchers compare observations with dynamical models and ask which combinations of bar speed, spiral structure, gravitational potential, and disturbance history can reproduce the measured patterns. That makes the Milky Way a laboratory in which the evidence is distributed across billions of moving test particles. The challenge is identifying which forces produced which signatures. The central bar is a particularly important unknown because its rotation influences a large region of the disk. A bar is not simply an elongated pile of stars sitting motionless at the center. It is a rotating pattern. The rate of that rotation affects where resonances occur and how stars and gas respond. Measure the bar's pattern speed incorrectly, and interpretations of structures elsewhere in the galaxy can shift. Different methods constrain it from different directions: stellar motions, gas dynamics, the distribution of stars in the inner galaxy, resonance signatures in the disk, dynamical models. The goal is not merely to determine how fast the bar turns. It is to understand how that rotating structure has exchanged energy and angular momentum with the rest of the galaxy. That exchange may influence the long-term evolution of the disk. Spiral structure creates an even harder version of the same problem. The textbook picture encourages us to imagine one stable spiral pattern rotating coherently for billions of years. Real disks may be more complicated. Spiral features can change strength. They can branch, they can reconnect. They may not all share one long-lived pattern speed. Some may be generated or amplified by interactions between the disk and other structures. If so, predicting the exact appearance of the Milky Way's spiral pattern far into the future becomes fundamentally different from predicting the orbit of a planet around the Sun. The galaxy is reorganizing itself. That does not mean prediction is impossible. It means prediction becomes probabilistic and model-dependent. Astronomers can calculate how populations should respond under particular gravitational conditions. They can test whether a model reproduces measured positions and velocities. They can compare multiple models. They can identify quantities that remain stable across reasonable assumptions and others that do not. The uncertainty becomes part of the map. This is one of the quiet revolutions of modern galactic astronomy. A good map no longer tries to hide uncertainty behind a clean line. It can show where distances are precise and where they are weak, where a spiral feature is anchored by geometric measurements and where it is extrapolated, where stellar motions strongly constrain a dynamical model and where several models remain possible, where an accretion event is supported by multiple chemical and kinematic signatures, and where the identification is more tentative. The unfinished areas are scientific information. They tell us what measurement should come next, and the Gaia mission itself illustrates that process. Its spacecraft has finished observing, but the scientific map produced from those observations is not finished. Years of measurements have to be calibrated and processed together before their full precision can be extracted. Future catalog releases from the same mission data will improve stellar motions, identify more complex sources, and provide longer time baselines than earlier releases could use. The telescope can stop observing while the map continues to improve. That is possible because precision astrometry depends heavily on time. A star's position is one measurement. Its proper motion is a change in position. The longer the observational baseline, the more clearly slow motion can separate from noise. Binary stars can reveal orbital behavior that shorter datasets blur together. Variable sources can expose patterns that require repeated measurements. Tiny accelerations can become detectable. The same photons already recorded by the spacecraft can therefore support a richer galactic reconstruction when processed as a longer, more complete time series. Even then, Gaia will not produce the final map. No mission can. Future infrared astrometry could reach populations hidden from optical surveys. Radio interferometry can continue anchoring distant star-forming regions geometrically. Spectroscopic surveys can add chemistry and radial velocities. Infrared telescopes can push through obscuration toward the inner disk. Neutral hydrogen and molecular line surveys can trace gas where stars provide only part of the structure. The next map will be built by combining them. Then another map will replace it. Not because the previous one was a failure, because precision exposes structure that simplification concealed. The Milky Way once looked like a luminous band, then it became a disk, then a spiral, then a barred spiral. Now it is a warped, flared, rippling, accreting, dynamically perturbed system whose visible structure sits inside a much larger gravitational halo. Each improvement made the drawing less simple and more real. Yet there is one perspective no amount of precision from Earth can provide. We can reconstruct the galaxy from within. We can measure its stars, we can infer its arms, we can model its motion, but we cannot compare that reconstruction with the one observation that would seem to settle the shape immediately. A photograph taken from far above the Milky Way. The distance required to obtain that view reveals just how deeply trapped inside our own map we really are. To photograph the Milky Way from the outside, a spacecraft would first have to escape something much larger than the solar system. It would have to escape our point of view. The difficulty is not simply reaching interstellar space. Voyager has done that. The difficulty is traveling far enough that the Milky Way stops filling the sky around the spacecraft and begins to look like one object. Those are completely different scales. The stellar disk of the galaxy spans on the order of 100,000 light-years, depending on exactly which population and boundary are being measured. The Sun is embedded within that disk, tens of thousands of light-years from the center. Move a spacecraft a few hundred astronomical units from Earth, and the constellations barely change. Move it a light-year, and the nearest stars shift noticeably, but the galaxy still surrounds the observer. Move it hundreds of light-years, and our local stellar neighborhood begins to look different. The Milky Way still does not become a face-on spiral. To see the disk from well above its plane, a spacecraft would need to travel not merely outward from the Sun, but thousands or tens of thousands of light-years in a direction roughly perpendicular to the galactic disk. Only then would the geometry begin to resemble the external views we obtain of other spiral galaxies. At current spacecraft speeds, that is not an engineering project in any familiar sense. It is a timescale problem so large that ordinary mission language begins to fail. Voyager 1 travels through space at roughly 17 kilometers per second relative to the Sun. At that speed, crossing 1 light-year would take roughly 18,000 years. 10,000 light-years would require roughly 180 million years. The precise number is not the important part. The important part is the scale change. The journey needed to obtain a clean external portrait of the Milky Way is not longer than a human lifetime. It is longer than the existence of Homo sapiens by an enormous margin. It reaches into geological time, and even if a future civilization developed spacecraft moving at a significant fraction of the speed of light, the problem would remain immense. At 1% of light speed, 10,000 light-years still requires about 1 million years in the rest frame of the galaxy, ignoring acceleration and other practical constraints. At 10%, it still requires roughly 100,000 years. The external photograph that seems like the obvious solution is therefore not a realistic near-term scientific strategy. We cannot simply leave the galaxy, take a picture, and compare it with our reconstruction. We have to infer the structure from within. This makes the Milky Way unusual among the astronomical objects we study. For many nearby galaxies, the global shape is the easy part. A telescope sees the whole disk at once. Spiral arms can be traced across large angular scales. A central bar, if prominent, is immediately visible. Warping may be measurable. Interactions with neighboring galaxies can be seen in tidal tails or distorted outer structure. The cost is distance. Individual stars become difficult or impossible to study in the same detail. For the Milky Way, the trade-off is reversed. We have access to exquisite local information. We can measure motions of individual stars. We can examine their spectra. We can estimate their ages. We can analyze chemical abundances. We can identify stellar streams one star at a time. We can resolve the orbits of stars near the central black hole. But the global geometry has to be reconstructed indirectly. We know the galaxy deeply. We do not see it whole. That distinction may be one of the most important things to understand about modern galactic astronomy. It explains why external galaxies remain useful even when the Milky Way provides far more detailed local data. They offer perspective. Astronomers can observe barred spirals from above and compare their structures with dynamical models of our own galaxy. They can examine how spiral features connect with bars. They can study warps in disks without being embedded inside them. They can look for galaxies whose stellar masses, star formation rates, bar structures, or environments resemble particular aspects of the Milky Way, None of those systems is a perfect twin, but together they provide a library of possible configurations that helps constrain what our own reconstruction should physically resemble. The comparison also exposes a subtle risk. Once a familiar artistic representation of the Milky Way becomes widely accepted, it can begin to feel like direct evidence. A clean spiral diagram may contain four smoothly connected arms because that is one useful interpretation of several datasets. The next generation of measurements may break one arm into segments. A feature once drawn as minor may become more prominent. The bar may be revised. The warp may become more complex. The outer disk may extend differently in different stellar populations. A map can be scientifically responsible and still be temporary. That is normal. Every serious map carries a date, whether the date is printed on it or not. The Milky Way's map is especially sensitive to this because several major observational programs are still turning raw measurements into deeper structure. Gaia's observing phase is over, but the full value of the mission is not contained in the catalogs already released. Longer baseline processing improves proper motions. More complete treatment of binaries and variable sources changes how some stars are classified and measured. Better calibration can sharpen the astrometric framework itself. Ground-based spectroscopic surveys continue adding radial velocities and chemical information. Radio arrays continue measuring masers and gas. Infrared observations continue penetrating regions where visible light performs poorly. And future surveys will add enormous numbers of faint stars and time domain measurements across the sky. The future Milky Way map will not come from one replacement for Gaia. It will come from combination. Astrometry provides geometry and motion. Spectroscopy provides velocity and chemistry. Infrared reveals obscured populations. Radio astronomy anchors distant star-forming regions and traces gas. Time-sane surveys reveal variable stars and transient behavior. Dynamical modeling tests whether all of those measurements can belong to the same gravitational system. Each method compensates for another method's weakness. That is the only practical route to completeness. And even then, there will be limits that better instruments cannot erase completely. There will always be regions where direct distance measurements are difficult. There will always be extincted and crowded lines of sight. There will always be ambiguity in reconstructing ancient orbital history. There will always be uncertainty in separating overlapping dynamical effects. And there will always be a difference between what can be measured now and what must be inferred from a model. The goal is therefore not a perfect picture. It is a map in which the uncertainty itself is measured. That changes what progress looks like. A new survey does not need to replace the entire Milky Way diagram to matter. It may reduce the uncertainty in the distance to one spiral segment. It may reveal that a supposed continuous structure is actually disconnected. It may show that stars assigned to the halo belong to the flared disk. It may sharpen the pattern speed of the bar. It may discover that a stellar stream was perturbed more strongly by the large Magellanic Cloud than earlier models assumed. Each change rearranges a small part of the larger reconstruction. Eventually, those corrections alter the picture. This has happened repeatedly. The Milky Way was once imagined as a much smaller stellar system centered near the Sun. Then the scale shifted. The galactic center moved far away from us. The disk grew. Spiral structure emerged through radio and optical work. A central bar became unavoidable. The halo became gravitationally dominant at large scales. Gaia turned the stellar disk into a moving, chemically layered record of mergers and perturbations. The map did not become less scientific each time it changed. It became more constrained. That is the deeper meaning of an unfinished map. It is not evidence that astronomers know too little to describe the galaxy. It is evidence that the description has become precise enough for disagreements to become visible. A century ago, the uncertainty was the overall scale. Now, some of the unresolved questions concern the exact shape of the bar, the continuity of individual spiral features, the origin of specific disk waves, the structure of the dark halo, and the ancient merger history recorded in stellar phase space. The frontier has moved inward from the existence of the galaxy to its detailed architecture, And that brings us back to the image we started with. The face on Milky Way on a screen. The blue spiral arms, the bright center, the small marker showing the sun. The image is not a photograph, but that no longer makes it less impressive. It makes it more impressive. Because every curve on that map exists only after someone found a way to measure across dust, distance, motion, crowding, and perspective from a position buried inside the disk. The final question is no longer why no one has photographed the Milky Way from outside. It is how much of that external view we can reconstruct without ever leaving home. The answer is surprisingly much, not everything, but enough that the Milky Way has become one of the most precisely investigated large systems in astronomy, even though no human being has ever seen it from the outside. That achievement depends on resisting the temptation to confuse a clean image with complete knowledge. The galaxy does not give us one privileged view. It gives us fragments, distances, velocities, spectra, dust maps, radio emission, stellar ages, chemical abundances, parallaxes, variable stars, masers, streams, warped disks, perturbed orbits, dark matter constraints. Each fragment answers a different question. The map emerges only when those answers agree, and where they do not agree, the disagreement becomes part of the science. This is why the Milky Way should not be imagined as a solved object with a few missing details. It is better understood as a system whose broad architecture is well established, while some of its most interesting internal structures remain under active reconstruction. We know we live in a barred spiral galaxy. We know the sun occupies the disk far from the center. We know the galaxy contains multiple spiral features traced by gas, young stars, and other populations. We know the disk is warped and flared. We know the stellar halo preserves debris from disrupted systems. We know the Milky Way is embedded in a much larger gravitational halo dominated, under the standard cosmological interpretation, by dark matter. We know satellite galaxies are still perturbing it. We know the galaxy has changed through mergers and will continue to change. None of those conclusions requires an external photograph. They come from measurement. But each conclusion carries a different degree of precision. The position of a nearby star can be known extraordinarily well. The exact continuation of a spiral arm behind the inner galaxy may be less secure. The motion of a particular stellar stream can be measured. The precise three-dimensional shape of the dark matter halo can remain disputed. A population can strongly suggest an ancient merger. The exact orbit of that long-destroyed galaxy may remain impossible to reconstruct uniquely. Scientific maps improve by preserving those distinctions rather than erasing them. That may be the most important change in how to read any modern image of the Milky Way. The smooth curves are not all equivalent. Some are heavily anchored by direct geometry. Some summarize the distribution of selected tracers. Some interpolate between measurements. Some represent the best current model where direct observation is difficult. The image is not one level of certainty. It is several levels compressed into one frame. And there is no single future observation that will suddenly remove all of that uncertainty. Gaia cannot see every star. Infrared telescopes cannot solve every distance. Radio interferometers cannot measure geometric parallaxes to every cloud. Spectroscopic surveys cannot recover the exact birth history of every stellar population. Computer simulations cannot replace missing measurements. Every method has a boundary. Progress comes from making those boundaries overlap. A star obscured in visible light may appear in infrared. A distant star-forming region that is difficult to place through ordinary photometry may carry a radio maser with a geometric parallax. A stellar stream whose shape is ambiguous may become more informative once its proper motions and radial velocities are measured. A model of the bar may be tested against both inner galaxy observations and velocity patterns near the sun. Independent evidence is what turns reconstruction into measurement. That principle extends well beyond the Milky Way. Astronomy is full of objects we cannot visit, touch, or observe from every angle. Black holes are inferred through the behavior of matter and light around them. Exoplanets are often detected because of what they do to their stars. Dark matter is mapped through gravity. The early universe is reconstructed from radiation that has traveled for most of cosmic history. The inability to stand outside a system does not make knowledge impossible. It changes the kinds of evidence that matter. The Milky Way is simply the most intimate example. We are not distant observers. We are embedded participants. Every telescope points outward from a position already inside the structure. Every distance begins here. Every galactic longitude is defined from here. Every velocity is measured relative to a local frame that must itself be understood. Our location creates extraordinary access and extraordinary bias at the same time. That contradiction will never disappear. Even a civilization with far more advanced instruments would still have to contend with geometry, unless it physically traveled far beyond the disk. And if it did, the external view would answer some questions beautifully while losing access to others. From far above the galaxies, spiral structure would become obvious. Individual stellar motions would become much harder to measure with the precision available from nearby. The perfect observing position does not exist. Every perspective trades one kind of information for another. We happen to occupy the perspective where local detail is exceptional and global form is difficult. So we reconstruct the whole from the inside. The result is not static. As new catalogs arrive, some distances will improve. Some stellar classifications will change. Some moving groups will separate into distinct populations. Some proposed arm connections may strengthen, others may weaken. New infrared surveys will expose stars hidden behind dust. Radio measurements will extend geometric anchors across more of the disk. Spectroscopic programs will add chemistry and radial motion to increasingly large samples. Dynamical models will become better at including the bar, spiral structure, satellite streams, and the time-dependent gravitational field together. The future Milky Way will probably look more complicated than the current one. That is what has happened every time the measurements improved. Greater precision did not simplify the galaxy. It revealed more structure. The disk turned out to contain multiple overlapping populations. The halo turned out to contain merger debris. The outer disk turned out to bend and ripple. The local stellar neighborhood turned out to carry dynamical signatures of distant structures. The large Magellanic Cloud turned out to be important enough to disturb the larger galactic system. The spiral pattern turned out to depend partly on which population was being traced. The more complete the map becomes, the less it resembles a perfect diagram. That is not a failure of astronomy. It is what a real galaxy looks like when measurement begins replacing abstraction. And eventually, this brings us back to the small marker printed on so many images. You are here. The phrase seems to locate us. In reality, it also explains the entire problem. We are here inside the disk, inside the dust, inside one local spiral structure, moving around the galactic center, surrounded by stars whose light reaches us from different distances and therefore different moments in the past. We do not occupy a balcony above the Milky Way. We occupy one moving point inside it. From that point, humans have measured enough geometry to determine where the galactic center lies, enough motion to reconstruct large parts of the gravitational field, enough radio emission to trace gas through obscured regions, enough variable stars and masers to build distance anchors across the disk, enough stellar chemistry to identify populations that formed in galaxies destroyed billions of years ago, enough stellar motion to see the disk still responding to disturbances, enough evidence to draw a galaxy no one has ever directly seen. That is the real achievement behind the familiar picture. The face on Milky Way is not valuable because it pretends uncertainty is gone. It is valuable because it compresses generations of indirect measurements into a form the human eye can understand. And the blank regions matter just as much as the filled ones. They identify where perspective still wins, where dust still wins, where distance still wins, where models are doing more work than direct geometry, where future observations can still change the picture. There may never be a final map in the strictest sense. The galaxy is moving while we measure it. Stars are being born, others are dying, orbits are changing. Satellite galaxies are falling inward. Streams are lengthening. The disk is oscillating. The bar is rotating. Spiral structure is evolving. Any perfect map would begin aging the moment it was completed. Perhaps that is why the most accurate picture of the Milky Way is not one final illustration. It is the process of reconstruction itself. A bright band in the night sky became a disk. The disk became a spiral. The spiral gained a bar. The bar entered a warped and flared disk. The disk entered a stellar halo built partly from destroyed galaxies. The visible galaxy entered a larger gravitational halo that cannot be photographed directly, and every layer opened another question. The map keeps expanding because the evidence keeps getting better. We live inside the Milky Way. That is why we cannot simply see it. And it is also why we can measure it with a level of detail no distant observer ever could. From inside the unfinished map, we are slowly learning what the whole thing looks like.